Hello, in this video we're going to be talking about semiconductors and covalent network solids and semiconductors. So a covalent network solid is a extended solid formed from nonmetals or metalloids. Okay, so these are going to be things where we have covalent bonds connecting all the atoms together. And this big hunk kind of looks like this. So this is what diamond looks like. Diamond would be an example of a covalent network solid made by a bunch of carbons bound to another bunch of carbons. And here, with our covalent network solid, we show the empirical formula. Instead of our molecular formula. Because it'd be really hard to show how many atoms are in diamond, for instance. Really depends on the size of the diamond, right? So some properties. Because we have a very extended structure, we're usually talking about hard, high-melting substances. And again, this is usually a somewhat brittle substance, but it's very hard, so it's hard to break. And as a note to melt, we need to break covalent bonds. Not an easy thing to do. So we've got atoms beyond count. So we have lots and lots of covalent bonds holding it all together in this beautiful structure. And just like we saw with our metallic solids, when we have an extended structure, we have orbitals overlapping each other. So all the atoms together are going to have all of their orbitals overlapping. We have atoms beyond count. Bonded together. Therefore, we have orbital overlap between all the atoms. So, just like we saw with our metallic solid, and we see the same thing in an ionic solid, but we get bands of energy. Or bands of orbitals, rather. So we're going to have a valence band. This is going to be the overlap of our bonding molecular orbitals. And this is going to be filled. And then we're going to have our conduction band. And this is the overlap of our anti-bonding molecular orbitals. I'm just going to do MOs. And this is going to be unfilled, or empty. Okay. Now, we didn't see a difference. So with our valence band and conduction band with a metal, there's going to be an overlap between those. But with a metalloid or a non-metal covalent network solid, we're going to have a band gap. So a gap between the valence band and the conduction band. I will often write this as EG. Yeah, like I said, it's a gap, the energy gap specifically, between the valence band and conduction band. So VB valence band, CB conduction band. Okay. So, as I said earlier, the band gap itself, if we have a metal, is non-existent. So we have no band gap. That's because our valence band and conduction band overlap. Other extended solids do have a band gap. So we have ionic solids. They generally have a large band gap. And then we have covalent network solids. And within our covalent network solids, we have non-metal covalent network solids. These are going to have a large band gap as well. And then we have our metalloid covalent solids. And these are going to have a smaller band gap. Okay. So what's going on with the metal? In case you didn't see the video about metallic bonds, we start out with a single atom with a large gap between a filled orbital and an unfilled orbital. So this would be our HOMO and LUMO. Okay. As we get more atoms that have overlapping orbitals, because they are bonded to each other, they're going to start decreasing this gap, decreasing the HOMO-LUMO gap. And after we get enough of them together, in the case of a metal, we get bands. So this, or the case of an extended solid, we get bands. Now what's shown here is a metal. And we can tell it's a metal because there's an overlap between our valence band and our conduction band. Remember, our valence band, that's where our valence electrons are. Our conduction band, that's where we have to put electrons in order to conduct. Okay. Now, we're going to look at different size band gaps. So we've already looked at metals. We've kind of exhausted that already from a previous lecture. But today we're going to look at extended solids that actually have band gaps. And we're going to look at binary and atomic. So atomic, generally your conduction, or with an atomic, your conduction band and your valence band is coming from one species. With a binary species, your conduction band is coming from a different atom than your valence band. Okay, generally. So let's start out with our conductors, just to keep everything, cohesive. So band gaps, type of substance. So if we have a band gap, our band gaps will tell us what type of substance we have. First, if we have a conductor, we have no band gap. Right? So this is going to be our metals. And here we can conduct electrons without the addition of any energy because the two bands are overlapping. We then have something called a semiconductor. It can semiconduct. So this is going to be a small band gap. between our valence band and our conduction band. And here, within here, we have metalloids. And then some non-metal covalent network solids. Okay, so both of them are covalent network solids, either metalloid covalent network solids or non-metal covalent network solids. But generally non-metals are actually going to be in the class called insulators. And here we have a large band gap. And these are going to be most non-metal covalent network solids. I'm just going to be lazy, CNSs. And ionic solids. Okay. Some notes. Our semiconductor will conduct electrons upon the input of some energy, whether it be thermal or photoenergy. Insulators don't conduct electrons, or they require a very large amount of energy, so they insulate as opposed to conduct. A note about ionic solids. So, as I said, these are insulators. And the reason that these are insulators is because our valence band, so where we have our electrons at, this comes from our non-metals, or non-metal orbitals. While our conduction band, so this is going to come from where we're missing electrons, right? So this is going to come from our metal orbitals. And as such, these generally don't have very close energies, which is why we result in such a large band gap there. And then with our nonmetals, generally they're smaller, more electronegative, so they're going to have greater orbital overlap, and that greater orbital overlap will result in a greater change in, or a greater gap between HOMO and LUMO, or in this case, our valence and conduction bands. Okay, so here is just a visual, and actually this is our insulator. So conductor, this is our metal, semiconductor, metalloids, some nonmetals, and then insulator, ionic compounds, and most other non-metal covalent network solids. Okay, so let's look a little bit more at our semiconductors. Our semiconductors are formed from group 4 elements. So 4A. So this includes silicon, germanium, so on and so forth. So those are going to be our semiconductors in the elemental form. So elemental semiconductors. We can also have binary semiconductors. So with our group 4, those are kind of our metalloids. Our binary semiconductors, these are going to be group group 3A, 5A substances. So our first element comes from group 3A, our second element comes from group 5A. So this includes indium phosphide and gallium arsenide. Okay. We can also have binary semiconductors that are group 2B, 6A. Okay. These are going to be things like cadmium selenide and zinc telluride. The thing to note, in each one of these cases, so this has 4 valence electrons, and then these are going to average to 4 valence electrons. So we need that 4 valence electrons is kind of the key so that we can make the correct number of bonds and have the correct type. Okay, so once we have our semiconductor, we can kind of predict the relative band gap, or compare substances to determine which one's going to have a larger band gap. So we can predict or compare our band gaps. So we generally look about what's going to increase the band gap. So the following conditions will result in a band gap increase. So, first thing, elements that are higher up on the periodic table are going to have a greater band gap than things lower in the periodic table. So we can compare silicon versus germanium. Okay. Silicon is going to have a larger band gap because it is higher up on the periodic table. And then germanium is going to have a smaller band gap. So silicon has a band gap of 1.11 electron volts, while germanium has a band gap of 0.67 electron volts. So EV is electron volts. We can also look at binary in the same way. We can compare zinc selenide versus cadmium telluride. So zinc selenide will have a larger band gap. Cadmium telluride would be smaller. Okay. Zinc selenide has a band gap equal to 2.58 electron volts. And then cad telluride is at 1.50 electron volts. Okay. Then here's a chart summarizing all of that. Another way that we can affect our band gap is by looking at our basically electronegativity differences. So a greater electronegativity difference, delta En, greater difference in electronegativity, results in a greater band gap for binary semiconductors. If our electronegativity difference is great enough, we form an ionic compound, and hopefully you guys remember that ionic compounds are insulators, not semiconductors. So when we get a greater electronegativity difference, we're going to basically increase the ionic character of the bond. Which will make it closer and closer to that ionic type of electron or band gap. Okay. Now, once we have a semiconductor, we can do stuff to it to change it. So we can dope semiconductors. A undoped semiconductor is called an intrinsic semiconductor. And then if we dope it, if we add something in to change our band gap, we are going to get an extrinsic semiconductor. Okay. And a dopant is going to be an atom added to the semiconductor to change the band gap. And when we change the band gap, we change the electronic properties. Okay. So we have two types of doped semiconductors. We have an N-type, which we call a negative type. And this is made by adding in a dopant that has more valence electrons than the host or intrinsic semiconductor. The host is the thing you're doping into, so the intrinsic. Semiconductor. Okay. Here we have more electrons, and when we add more electrons in, we add a donor level into the conduction band. Okay, just gonna. Okay, our next type is P-type, or positive type. And this time we add a dopant in that has fewer valence electrons. And when we do that, we add in a acceptor level into the valence band. So it adds a hole, or acceptor level, in the valence band. Okay, so let's real quick look at this. So we can take pure silicone. We can add in an element that has a greater number of valence electrons. So silicone itself is 4A. If we add in something from 5A, that has one more valence electron, and we produce an N-type semiconductor. So for instance, phosphorus added into our pure silicone adds an extra electron into the structure. That energy of that electron, that energy level from the electron, is added into the conduction band, and we form a smaller band gap. So now the electron just has to go from that donor level into the conduction band, which is a much smaller energy difference than if we were going from the valence band. If we want to form a p-type, we need fewer valence electrons. So in this case, we're going to add in something from 3A. Okay, something like gallium. Gallium doped into silicone has one fewer electron. So we form a acceptor level. So an unfilled, so this is unfilled. This is filled. So that acceptor level now has an area for electrons from our valence band to go up and excite there. So now, again, we have a smaller band gap. Okay. So that's everything for our semiconductors.